Okay, so we're going to start a new unit today. We're going to start by talking about something called a piecewise function. A piecewise function is, well, we'll talk about what it means in a second. But our sort of our goal, we won't get through all this stuff today, but maybe today and the next time we meet combined, we're going to learn what a piecewise function is. We're going to learn how to evaluate piecewise functions. We'll do that today. That's not a big deal. The bigger deal, and this is kind of our goal for today, is see if we can get to a point where we can graph piecewise functions. If we can get that done, we've covered a lot of ground. That would be good. And then there's a specific kind of piecewise function called a floor function that I'll just show you next time we meet. And I'll show you how to use technology. And I don't know if we're really going to do any application stuff up for this. I don't know if it's that big a deal. I'm going to describe one to you, but that's probably good enough. Okay, I don't know if we'll actually attach the math to an application for this stuff. So first of all, a piecewise function, and if you want to pull your notes out, this is just the first section of Unit 3. Okay, so a piecewise function is made up, it's a function that's made up of two or more individual functions, the pieces of the function, right? It's in different pieces, and each of these pieces of the function has its own domain, so its own place where it exists. It's the x values where it exists. So, for example, we've got this. Let's look at this top example up here. We have f of x is equal to, now this looks weird. This is how we write a piecewise function. There's a couple parts to this. The first part is we're going to have this open script bracket that's open to the right. When you see that in math, when I just see this part right here, let me cover some stuff up for a second. If all I see is that, then I know that I'm going to have a piecewise function, and f of x is going to equal, I'm going to get multiple rows here. Each row of the function is going to be a different piece of the function. There could be two, there could be three, like there is in this case down here, right? Notice on this one down here, I've got a bigger bracket, and the only reason I have a bigger bracket is I've got to have room for three rows instead of two. So there are three pieces to this number two, this function number two, whereas there are only two pieces to this function in example 1. Okay. All right. So why might we do this? First of all, okay, this is something in life that happens all the time. All the time in life, we look at situations where things change suddenly. Okay, let's take an example, like if a person were skydiving. Let's say you're skydiving out of a helicopter. Okay, you're going to jump out of a helicopter that's at extremely high altitude. Think about what that's going to feel like when you jump out of that helicopter. You're going to jump out of the helicopter, and immediately you're going to feel your stomach just, you know what that feels like on a roller coaster, right? When your stomach drops, when you're in free fall and you're accelerating and you're picking up speed, and the air is going to start to whoosh by you faster and faster, right? We'll call that part A of our journey. Okay, after a while, though, as I fall, what's going to happen? Am I going to continually accelerate forever? What happens when you skydive? At some point, you stop picking up speed.
Terminal velocity.
Yeah, you hit terminal velocity. You guys have all probably heard about terminal velocity, right? So terminal velocity is where the air that's pushing up on you as you fly through the air, the upward force of that air against you matches the downward force of gravity, and that's as fast as you can go, right? And so you're gonna fall down at terminal velocity. So we'll call that part B of our journey. We accelerated for part A, then we got to terminal velocity, and we're just falling at a constant velocity. Okay, now we're getting a little too low, so we're going to pull the ripcord. When I pull the ripcord, what happens then? Noah, what happens when you pull the ripcord when you're skydiving?
Parachute comes out.
Okay, the parachute comes out, and that's going to be a pretty sudden and violent thing, right? You're going to get jerked upward because that parachute's going to catch the air, and it's going to pull you upward to slow you down, right? So there's going to be a period there of a few seconds where you're going to really get jerked in your harness, and you're going to get pulled up pretty violently and slowed down. But then after a few seconds, the parachute catches the air, and you're going to be drifting down at constant speed again. You hit a lower terminal velocity until you land on the ground, softly on the ground, right? So there really were four parts to our journey, right? Now think about this. What if we were going to try to come up with a math function where our input was going to be t? Instead of x, it's going to be t. So the amount of time that has elapsed since we jump out of the helicopter. So we're holding a stopwatch when we jump out. We start the stopwatch just as we step out of the helicopter, right? So time 0 would be right when we step out the door. And then time's going to run forward. Well, so that's our input value. Instead of an X, it's going to be a T. F in this case, instead of calling it F, let's call it something like H. So H for height. So we're going to come up with a math function that's telling us the height above the ground as a function of time. Well, that would have to be a piecewise function, wouldn't it? Because there were 4 distinctly different parts of our journey down to the ground from the helicopter. We would have to have 4 rows in our piecewise function. One row would correspond to when we're accelerating, when we first jump out. Another row would be when we're falling at terminal velocity. A third row would be where we deploy the parachute and we get jerked upward and slow down. And a fourth one would be where we're drifting at a slow terminal velocity down to the ground, right? So my only point here is you can see that there is a mathematical need for us to be able to have functions like this. And after all, what is math for? Usually in the real world, we use math to try to describe the way the world works, to make predictions based on some model, right? That's usually what math is used for, okay? All right, so we have a need for these piecewise functions. Let's kind of focus on how they work a little bit. So let's look at this top function up here. We're going to ignore the bottom one. So I'm just going to cover this one up for now so we're not confused. We're only looking at this top one up here. Let's break this into a couple parts. Let's look at, well, before we even do that, let's try to evaluate this function at some different inputs. Now, when we evaluate a function, you guys all know what to do there, right? When you see something like f of -5, you just know that you're plugging -5 in for x and seeing what I get, right? I'm just going to plug the -5 in every place where I used to have an x. Okay, what's the problem here, though? What's the problem in this case? What makes it just a little bit trickier this time, Madeline? When I want to evaluate this function f at -5, it's a little bit more difficult than usual. How come? You can type it in chat if you want to. Questions for Madeline. What makes this a little tougher, this piecewise function?
I don't know.
I mean, usually it'd be pretty easy. We just have an equation we plug it into, but this time I've got 2, right? That makes it tougher. I have to know, first of all, which piece am I plugging into, right? Well, if you look at a piecewise function, there are 2 parts to each piece of the function, to each row. The top row up here, and let's go ahead and I'm going to highlight this one in orange, just so we can know what we're talking about for a second here. So we're talking about the orange piece, that piece up there, right? Well, look, there's 2 parts to it. We've got the equation part. That's telling us, what equation are we plugging x into? That's telling us what the shape of this graph is going to look like. But there's another part, and that's the domain. It's telling us for what values of x does f of x have this piece? Where is an ant walking along this function going to be walking along the orange piece of the function? Only when x is less than -2. Okay, there's another piece to this function. We'll call that the purple piece. So the purple piece down here, right, that's a different piece. F of x is equal to a different function, 5x plus 3, whenever x is greater than or equal to -2. So for these purple input values, we're using the purple equation, right? So then let's look at this first example. If I want to, and this is going to be our red example. We'll kind of color code this whole thing here, right? So f of -5, which piece, the top or the bottom piece of the function, are we going to use for part A? Kinley, what do you think?
The top one.
The top one, good, right? The top one, because our input value, -5, is an x value that is less than -2, right? So at x equals -5, we're on the orange piece of the function. Everybody see that? Okay, so that's the piece we're going to use. Because -5 is less than -2, we're going to plug, that's supposed to be a -5 there. Whoops. I got to fix that. So that's supposed to be a -5, right? So we're going to plug the -5 in for x in the top piece. And so every place I had an x, I'm just going to replace it with a -5. So I'm going to get -5 squared, which is 25, minus 1, which is 24. So for part A, f of -5 is 24. That's my output value when I input a -5. Okay, what about let's skip over and do part C. What about part C here? I want to calculate f of 7. Muriel, which piece of the function am I going to plug 7 into, the orange or the purple?
It's gonna be the purple.
The purple, yeah, because 7 is an x value that's greater than or equal to -2, right? Because 7 is greater than or equal to -2, we use the bottom piece. So I'm going to get 5 times my x value of 7, which is 35, plus 3 is 38. Okay, so I use the bottom piece for that one. Now, what about the middle piece here? What if my input value is -2? Riley, what do you think about that one? Orange or purple piece?
Looks like purple.
Purple, yeah, because -2 is greater than or equal to -2. It's equal to, right? -2 is not less than -2, so it definitely falls in the purple domain. We're going to use the purple function. So we plug the -2 in for x, and we get 5 times -2 is -10, plus 3 is -7. Okay? Everybody give me a 1 to 5 on that. Just type it in chat or flash me fingers. Does that make sense? Get real quick. Good. Good. All right. So far, so good. Okay, so the next issue then is we want to graph these piecewise functions. Okay, so we want to graph these piecewise functions. So we're going to look at a new example here. This is g of x. It's got a top piece and a bottom piece, right? The top one, we're going to call that the blue piece, and the bottom one, we're going to call the red piece. Okay? Well, first thing we might want to do here is recognize that the red piece, let's go back a little bit. Let's start off by I think I got those backwards. I did. Whoops. Hang on, that was messing me up. There we go. Well, let's just graph these two functions first of all. The red piece is just a line, right? That's in slope-intercept form, mx plus b. So for the top piece, what is my y-intercept? What do you think, Carson? What's my y-intercept for that line in the top piece?
For
For
that one was like,
that red.
that one.
Yeah.
-7.
-7. Okay. So I'm going to put a point then. I know I'm going to have a point down here at -7. So -1, 2, 3, 4, 5, 6, 7. So there's a point. And what's my slope on this one going to be equal to, Aiden? There. What's my slope for the red piece?
Are you talking to me?
Yep.
Oh, -3.
-3. So I'm going to rise -3 and run 1, right? So I would go down 3 and over 1, but that's not very convenient. So let's reverse that. Let's go up 3 and back 1 to that point right there, maybe, okay? So I'm going to put another point right there. Would everybody agree that the slope between those 2 points is -3? Everybody give me a thumbs up on that or a yes? Okay. All right, so then all I've got to do is just connect and extend, right? And I've got, that's not a, my line's a little bit off there, it looks like, but you get the idea, right? So I guess I can fix that. Well, maybe I can. Let's see. Close enough. Okay, so there's my red graph. Everybody agree? Look good? It's just a line through those 2 points. What about my blue graph? That's an easy one. Y equals -5. Well, what's the y-intercept for that line? Anybody? What's the y-intercept for that line? It's mx plus b. Well, there's nothing times x, so x is 0, or the slope is 0, and b is -5, right? So that's just going to have a y-intercept at -5, 1, 2, 3, 4, 5, and a slope of 0, because 0 is what's being multiplied by x. So that one's just a horizontal line. And we also know that, don't we? If we have y equals a constant number, then we know that's a horizontal line where every y coordinate is -5. So there are my 2 shapes, right? Everybody agree? We good with that? We graphed the top and the bottom piece. Okay, but look, we've got these domains to consider, right? We've got these domains. So we know that x equals -1 is the place where we're going to transition from the top piece to the bottom piece, right? So one thing that's useful to do is to put a vertical line in there, a dividing line. Well, here's the vertical line, x equals -1, right? Everything to the left of that, those are going to be the x values less than -1. And so that's where we want to graph the red piece. Everything to the right of that vertical dividing line is where x is greater than or equal to -1. And so that's where we're going to graph the blue piece. Everybody see that? Okay, so it might be useful to think about it this way. Let's just shade everything over here red, because that's where the red piece lives. That's the domain of the red piece, are all the x values to the left of our dividing line at x equals -1. We'll shade the entire region over here blue, just to remind ourselves that that's where we're graphing the bottom piece, which is g of x equals -5. Okay, so then that means that even though a line goes forever, I'm really only going to pick the part of the line that starts at my boundary, right? I only get to graph this function in the red region. I only get to graph it where x is less than -1. It doesn't continue on to the right of my dividing line. Everybody see that? Everybody give me a 1 to 5 on that concept. That's kind of a tricky one, I think. Everybody get what I'm saying? Because this is a piecewise function, I only get to graph this red line to the right of my boundary line, or the left of my boundary line, because I'm only going to graph it where the x values are less than -1, and there's my x equals -1 boundary, right? And by the same token, I'm only going to graph the blue piece where x is greater than -1. So that's going to be over here to the right. So it only gets graphed over here. Everybody see that? Give me a 1 to 5 on that. Okay, I only get to keep my graphs where they're defined. Okay? The red one only gets graphed for the x values less than -1, so to the left of my boundary. Maybe this is the confusing part here too. Maybe the confusing part is, what do I mean by the boundary? Well, that's literally the line. I'm just going to write this in here. That's literally the line x equals -1. Right? That's that line right there, isn't it? That vertical line is just the line x equals -1. That's my boundary that separates the red from the blue pieces, right? To the left of that, we graph the red. To the right, we graph the blue. Okay, but what about the endpoints? We got to deal with the endpoints. The red piece does not include an equal sign, but the blue piece does. So what kind of an endpoint do you suppose I'm going to have to put, Jaden, on the red piece, on the red graph, if the red piece of the function does not include -1? Questions for Jaden? No, Jaden. How about Melinda? You can type it in chat if you want to. In other words, am I going to have to put an open or a closed endpoint on this red graph? Questions for Melinda? Okay, I'm not getting anything back from Melinda. How about Aiden? Aiden Bork. Open or closed endpoint. If the red piece is defined where x is less than -1, it doesn't include -1 for a value. So it's got to be open, doesn't it? Everybody see that? That's correct. The endpoint, the red endpoint, has to be, oh man, oh, there we go. The red endpoint has to be an open one. There we go. Okay, everybody agree? How about the right endpoint? Or the blue endpoint? The endpoint for the blue piece does include -1. So what do you think, Ethan? Open or closed endpoint for the blue piece?
Closed.
Closed. So there it is. That's our picture. Okay. Does that make sense to everybody? We graph the red piece, which is this line that we established, right? It had a y-intercept of -7 and a slope of -3. And so the graph of that red piece looked like that, right? There was our y-intercept, and then we used a slope triangle to get another point. We connected and extended. The graph of the blue piece was just the horizontal line at -5, but we can only keep the part of the red line that is to the left of our boundary at x equals -1, and we have to have an open endpoint because we're not including -1. The blue function, we're only going to include the piece of the horizontal line to the right of our boundary, and we are going to include that endpoint, so it's closed. Okay? Give me a 1 to 5 on that. Okay? Well, that's pretty good for piecewise functions. These normally are pretty tough for people to get the first time. You guys are doing great. Okay, so now the next part of this is we want to list the domain and the range of our function, our piecewise function. So let's start with the domain. So the values of x that are graphed for our function. Okay, I got what I think is kind of a cool way to do this here. So here's the red piece. What if I take this red piece and I'm going to, oh man, hang on one sec. I gotta, let's do that. There we go. Okay, so if I take this red piece and I want to figure out what the domain of the red piece is, right? What are all the x values? What are all the red x values? And I'm gonna graph those on the x-axis. So do you remember this? This will visually kind of demonstrate something we talked about earlier. Do you remember that earlier in the year I talked about one way you can do that is you could project the red piece of the function onto the x-axis. So I'm going to take this whole red function and I'm just going to drag it down and up. So that it's dragged literally onto the x-axis. If I drag it vertically down and up, do you see that that's what I create? Everybody see that? Once again, what did I do there? Right, all I'm doing is I'm going to take my infinite red line and I'm just going to drag it down, so we're going to squish it onto the x-axis. And it's just going to end up looking like that if I squeeze it vertically onto the x-axis, right? And we're going to take that endpoint with it, right? It's got an open endpoint at the right of that one piece. Okay, what about the blue piece? Well, if I take the blue piece and I drag that vertically onto the x-axis, aren't I just doing that? Just dragging it vertically up? Everybody see that? So combined, the red and blue pieces, they seem to shade in the entire x-axis, right? Where I used to have an open endpoint for the red piece, the closed endpoint for the blue piece is filling that in. And so what do I end up with? Well, I end up with one solid horizontal line. The whole thing is shaded, right? Everybody see that? And so we end up getting the domain is just all real numbers. It's just negative infinity to infinity. Right? Everybody agree with that? It's all real numbers, so that's our domain. In other words, an ant, there is no x value that an ant couldn't stand on for our function. Agreed? If the ant's walking along this function, when he gets to the x value of -1, he falls off of the red piece onto the blue piece and continues walking to the right. Give me a 1 to 5 on that. Does that make sense? Okay, so my domain is all real numbers. Okay, that's pretty good. Pretty good. Okay, what about the range? What about the range? Now our job is we've got to project all this stuff onto the y-axis. Okay, so I can do that. I could take the red piece and I could project that over onto the y-axis, and it would look like that. Everybody agree? If I project it onto the y-axis? And if I project the entire blue piece onto the y-axis, well, that's not very interesting. The blue piece, if I project it onto the y-axis, it just ends up looking like a single point, doesn't it? At x equals -5. Right? And so we end up with our, where is it? There it is. Right? So we end up with, if I shade both of those parts, the red and the blue, if I shade them purple, I get that piece and I get this point right there. So what's that say for the range then? Well, it's got two parts. What are the possible y values? Well, y could equal -5, or it could equal this interval that has a lower limit of -4 and goes up for forever, right? But we're not including that lower interval. So using interval notation, it would look like that. It would be x is greater than, but not equal to, just greater, or sorry, y is greater than -4. So we'd have parentheses, -4 is our smallest y value, and the range would go up forever to infinity, right? Everybody see that? If I squeeze this stuff, if I squeeze both of those functions onto the y-axis, everybody see that's what I'm getting? Right? If I squeeze those things over. Okay? And so that's my range. If I want to write that using intervals, it would have just looked like that. Remember when we used interval notation back at the beginning? We would have said y is equal to -5 or y is greater than -4. I've got those two parts. Give me a 1 to 5 on that. And we'll use this notation. We'll use the interval notation. Okay? Hey, that's pretty good. We're getting this stuff. Okay, last thing then. Last thing is I want to show you a shortcut. So think about what we did here. When we were graphing the function, we went through a bunch of steps. We went through this step where we first of all, we just graphed the red equation, right? We just graphed the equation, and I'll just type this in. We graphed the equation literally. We graphed the line y equals -3x, minus 7. Okay, we graphed that function over here. We graphed down here, we graphed the line. Down here, we graphed the line. Whoops, there we go. We graphed the line y equals -5. Okay, and then we had to, after we graphed those, we had to go back and only keep the parts of those graphs in the red domain and the blue domain, right? Well, we could have maybe skipped this step right here where we graphed the entire red line that goes forever and the entire blue line that goes forever. Why wouldn't we maybe just do something like this instead? What if we want to only graph the red piece of the piecewise function in the red domain? Let's just skip the part where we graph the entire line and then just erase the parts that don't exist in the red domain. Well, we could do that with a t-table, right? The red domain are all of the x values to the left of -1, so less than -1. So let's pick some convenient x values that exist only in the red region where the red piecewise function lives. Well, one that we probably want to pick is the boundary line, right? It's the boundary value, which is -1, because we want to know, would you guys agree that we want to know where does this red piece end when it bumps into the boundary at -1? That's kind of an important piece to be able to make this graph, isn't it? So that's at x equals -1. So I could plug -1 into my function, which I already did, right? -3 times -1 is +3 minus 7 gives me a -4. So that means I've got an endpoint at the coordinates -1, -4, right? But remember, the red region doesn't actually include -1. That's just an endpoint. So I'm going to make that one an open endpoint. And there it goes, -1, -4, right there. Everybody agree? Okay, let's pick another one. Let's pick another x value over here in this region so we get another point we can use to connect and extend to make our line. Well, why don't we pick something like -4? If I plug -4 in, -3 times -4 is +12 minus 7 gives me 5. So I've got another point at the coordinates -4, +5. So that's right there, right? Everybody agree? Okay. So there's 2 points. I can use those 2 points to just connect and extend and get my line. Okay, so I got to build a line here. Here's my line. Right, I'm starting there, and I'm just going to go through that line in this direction, and it's going to go forever in that direction, right? So I'll just put a little arrow on that for an endpoint, or to show that it goes forever. This is an excuse to play with all my toys here. I like this. There it is. There's the red piece. Everybody agree? In one step, right? I'm going to only pick points this time. I'm going to make a t-table and only pick points in the red region so I can just go right to the graph. Let's do the same thing with the blue. Well, the blue lives in the region where x is greater than or equal to -1. Well, let's pick the boundary. This is a pretty easy one, right? The output is always -5. So if I input a -1, it doesn't matter what x is. Y is always -5. So I'm going to get the endpoint -1, -5, right there. And because this does include the equal sign, I get to have a closed endpoint there. I'll pick another value. How about +4? It doesn't matter. If I plug 4 in, I'm still just getting back -5, aren't I? Right? Because the output, the y value, is always -5. And so I got another endpoint over here at +4, -5. And now I can just make my horizontal line. There it is. Goes forever to the right. So I better put an endpoint on that. Or an arrow on the end, sorry. Oops. There we go. And that's what it looks like. There's my graph. But using those t-tables, I'm only picking values in the blue domain and the red domain. It's a lot quicker. Okay, give me a 1 to 5 on that. Does that make sense? Okay, good. I think that's pretty good for today. I don't think I'm going to try to do anything more for today. I feel like that's a lot of stuff to throw at you. Okay, so I'm gonna go ahead and I want to make sure this assignment is up for you. Let me just make sure it is. In Math Excel. Okay. It is. I just made it visible. So I'm going to let you guys have, you got about 8 minutes here I'll let you start early on it. Just jump into Math Excel. It's the A.3.1 assignment. That's the one you want to be working on, okay? Get in, just do a couple problems real quick just to kind of get the feel of things. And next time we meet on Thursday, we'll go a little bit further with this, and I'll fill in the rest of the information so you can finish the assignment. But you could start it now, okay? But give me a 1 to 5. Are we good with all this stuff? Okay, this is normally can be a pretty confusing topic, but I feel like you guys did pretty well with this. I think these visuals help. This is the first year I've done it this way, and I think that really helped. I will make this video available ASAP, so you're welcome to go back and look at this video again. Would it be helpful would you prefer, I can't remember if I asked you this before, would it be helpful to have this on YouTube so you could drag it around a little more easily and things? And is that, or does it make any difference to you? Are the videos the way they are? Is it okay, or would you prefer it? Riley, you definitely would prefer if it were on YouTube rather than the way it is right now. Anybody else feel that way too? Okay, I'll start putting these up on YouTube as well, okay? For now, it'll first show up the way it normally does, but then I'll put a link in there to my YouTube channel, and you'll be able to see all the videos on there as well. I'll start putting them all up on YouTube. I feel like YouTube is a better way to look at them. I think it's just more bulletproof. I feel like it works better. So I'll start putting them on YouTube for you. Okay, good job, everybody. I'm going to let you go a few minutes early and get started on the homework. Have a great day. I'll be here after school if you have questions. Otherwise, I'll see you on Thursday.